Greetings, Internet users. The topic I'm going to discuss with you today is basic astronomy. However, many people wonder how it's possible for the Sun to attract Earth without Earth falling directly into it. Since ancient times, we have known that Earth orbits around the Sun. Initially, it was believed that Earth's orbit was a perfect circle, but we now know that it's an ellipse. This means that Earth is sometimes a little closer to the Sun and at other times, farther away, with a difference of about 5 million kilometers more or less. This difference is relatively small to cause a significant effect on the planet's temperature. But why does Earth orbit the Sun, and what keeps it in that position? Basically, Earth maintains its orbital speed, also known as centripetal force, which is a type of acceleration that sustains circular motion. Let me explain what this centripetal force is. It might sound complicated, but it's actually straightforward. Any object with mass creates gravity, and at the same time, it experiences a centripetal force. Objects tend to move in a straight line towards the object attracting them, in this case, the Sun. However, they also move through space, causing continuous changes in direction due to the velocity's direction in the empty space. Every object maintains its constant velocity unless there are forces that modify it. This is described by Newton's first law, known as inertia. As a result, circular paths are formed, and this leads to a centripetal acceleration caused by the changes in direction. This means that if Earth and the Sun were fixed in space, there would be no changes in direction, and Earth would collide with the Sun. In this case, the changes in the Sun's direction force Earth to adopt a continuous circular trajectory in space, revolving around the Sun while, at the same time, following it on its orbit through the galaxy. The orbit of a celestial body occurs when it has enough velocity to maintain a speed similar to that of the larger mass body. This is a topic I explained to you earlier and can be perfectly applied to the Sun, the Moon, and other planets. Earth is continuously falling towards the Sun, but its velocity is sufficient to match its curvature and keep that dance going without them touching or separating. However, this dance can be disrupted either by a cosmic collision or a significant loss of mass. This principle applies not only to planets, but also to spacecraft. When a rocket leaves the atmosphere, it imparts a centrifugal force, which opposes the centripetal force that tries to move the spacecraft away from its curvilinear trajectory. The interplay of gravity and centrifugal force creates the centripetal force, preventing the spacecraft from being shot off the planet. In other words, in a curved trajectory, the centripetal force tends to pull towards the center of the sphere, and the centrifugal force pushes away from the center due to inertia. For a stable and circular orbit, both forces must be balanced. For example, when Oumuamua visited the solar system, it didn't get trapped in an orbit around the Sun because the asteroid/comet carried an enormous velocity from interstellar space and exceeded the Sun's escape velocity. Orbital dance is not possible in such a scenario. In the case of an artificial satellite orbiting Earth, the centrifugal force imparted by the rocket at launch precisely balances the centripetal force, which, in this case, coincides with the force of gravitational attraction. As a result, the satellite remains revolving around our planet. Thus, Earth's orbit is an almost circular ellipse, bringing confusion to ancient astronomers who believed in a perfect firmament with Earth at the center and circles as the geometric shape of creation. However, the heavens are not perfect and beautiful merely to fit our theories and beliefs. They are simply suitable to sustain our way of life. A circular orbit generally has a constant speed, but being an ellipse means there are moments in Earth's orbit when it moves faster or slower around the Sun. For instance, when Earth is closer to the Sun, known as perihelion, around early January, it moves faster at 30.75 kilometers per second. Conversely, at aphelion, around early July, when Earth is farther from the Sun, its speed decreases to 28.76 kilometers per second. On average, Earth's speed is approximately 29.8 kilometers per second. You might wonder why we don't notice this change in speed. That's because the change occurs gradually and is imperceptible. To understand this better, let's refer to Kepler's laws. Earth reaches its maximum speed and closest approach to the Sun during perihelion, which happens around early January. On the other hand, it reaches its minimum speed and farthest distance from the Sun during aphelion, which occurs around early July. Consequently, Earth spends 6 months either decelerating or accelerating, and that's why we don't perceive the change in speed. Similarly, the Moon follows an elliptical orbit around Earth. Sometimes it's a little closer to Earth, and at other times, it's a bit farther away. When it's farther away, it achieves its minimum orbital speed, and when it's closer, its speed increases. However, the Moon's orbital velocity prevents it from falling directly onto Earth. All the bodies in the solar system are governed by these laws. What would happen if Earth's orbital speed around the Sun decreased? It would get closer to the Sun, and as it gets closer, its orbital speed would increase at its nearest point. If we continued to decrease that speed, the orbital dance would lose its balance, and Earth would fall into the Sun. The nearly circular trajectory of Earth around the Sun allows for a stable climate on our planet, with seasonal changes primarily influenced by the varying axis of rotation. Earth has one of the least eccentric orbits in the solar system, meaning it's close to being a perfect circle. If our world had a highly eccentric orbit, with a pronounced ellipse, the climate changes would be significant, and life as we know it might not have been possible. We would experience drastic temperature fluctuations, with much more severe seasons depending on the type of orbit we had at mid-latitudes. For instance, summer temperatures could average around 50 degrees Celsius, 122 degrees Fahrenheit, when Earth approaches the Sun more closely, while winter temperatures could drop to at least minus 30 degrees Celsius, minus 22 degrees Fahrenheit. However, these temperature changes would occur months after the minimum and maximum approaches, as Earth needs time to warm up or cool down. Now you have an idea of why planets don't end up falling into the Sun and burning up. It's similar to when you hold a weight at the end of a rope and spin it. You'll notice that you're attracting the weight with your hand. Similarly, even though the Sun attracts the planets, their orbital motion has the right velocity to keep them rotating. If the Sun didn't exist, the planets would be sent flying, since the combined force of gravity and their velocity in space is what keeps them in almost circular orbits around the Sun. This is why the Sun and the remains of the planetary nebula during the formation of the solar system already had an orbital motion counterclockwise. Otherwise, all the remnants and forming planets would have crashed into the Sun from the beginning. This is called the conservation of angular momentum. What we do know for sure is that nothing in space is at rest, nor is it uniform or completely homogeneous. The initial stages of the formation of our solar system and other stellar systems are the result of chaos. The truth is that we maintain an almost constant speed relative to the Sun, with very subtle variations in speed. Although it may seem like we are not moving, we are constantly in motion, approaching and receding from the Sun, but without falling into it. The skies may not be perfect, but there is an unusual harmony in our solar system, a system of planets so ordered and controlled, which is not very common in other exoplanet systems. Amidst the chaos that abounds in many parts of the cosmos, there are some regions like our solar system that exist in isolation and order. We are like a speck of dust in a universe that increases its entropy, like a gas expanding infinitely. If you enjoyed this video, give it a like, and don't forget to subscribe. Share it on social media and leave your comment.